Hi, kiddos. We're going to pick up on Teacher Made Packet, page 50. And the next few slides, there might be one of the simple machines or something out of place, like out of order, but I will try really hard to make sure that they are in order so that you can get them all. So first of all, let's review quickly. The 6 simple machines are what's on the screen now. There's lever, inclined plane, wedge, wheel and axle, pulley, screw. So simple machines are found almost everywhere we look. At the bottom of page 50, we have inclined plane. So let's begin by watching a video on inclined plane.
Dear Tim and Moby, who invented ramps? From Allison. I'm not sure that there was one single person who invented the ramp, but anyone who's ever used one understands why they're so great. A ramp is one of the most basic examples of a simple machine called the inclined plane. No, not a plane like an airplane, a plane like a surface. As Moby here can probably tell you, an inclined plane makes work easier. To understand why, we need to understand the concept of work. Work is the effort exerted over a certain distance. The work needed to perform a given task is always the same, but the distance and effort can change in relationship to each other. If Moby wanted to, he could bypass the ramp he's using and jump straight up onto the platform. This is a pretty short distance, but it means he has to expend a lot of effort in one short burst. Even a robot can't keep that up all day. An inclined plane like a ramp increases the distance. That means the effort is spread out, and Moby can move boxes from now until doomsday without getting too tired. He does have to walk further. So, if you increase the distance, you decrease the effort. If you decrease the distance, you increase the effort. And the amount of work always remains constant. It's a trade-off. You're not getting anything for free here. You can find the inclined plane everywhere, in ramps and doorstops and axes and even screws. Well, the threads on a screw are really just a long ramp wrapped around a piece of metal. And that's the inclined plane. Well, I don't know. I thought you moving all these boxes full of bricks would be a good demonstration for the inclined plane. You have to put them back now. Hey, Moby? Let me out.
For notes for inclined plane at the bottom of page 50, we have a slanted surface or ramp, flat surface with one end higher, makes moving objects easier. So please pause the video and write these 3 things down, then resume the video and continue taking notes. All right, so now we're going to discuss the lever. So when you push down on your seat, which is that force, you lift your friend, which is the load. You have a fulcrum, which is going to be the middle point, which makes the seesaw move. And this makes it much easier to lift your friend. We're going to first watch a video about a lever, or as some people call it, a lever, and then we will continue with taking notes.
Dear Tim and Moby, we're learning about levers in science and I'm totally confused. Can you explain them? From Carlo. I think Moby just got a taste of levers in action. Levers are pretty simple, really. They allow us to move things more easily by magnifying our efforts. A lever has four components. The lever itself is a length of relatively stiff material. The fulcrum is the point on which the lever balances or pivots. The load is the weight or resistance that needs to be overcome, and the effort is the force you apply to the lever. These elements can be rearranged to make three kinds of levers. This is a Class 1 or first-class lever. The fulcrum is positioned between the effort and the load. A seesaw is a good example of a Class 1 lever, so is an old-fashioned scale. The thing to remember with levers is that distance and effort are interrelated. If you're willing to increase the distance over which you exert force, then you can decrease that force and still get the job done. It's like the difference between lifting a safe straight up over your head and pushing it up a hill to the same height. The total amount of effort expended is the same in both cases, but pushing it up the hill lets you extend the effort over a longer distance so you don't have to push as hard. Take a look at this simple Class 1 lever. See how the fulcrum is in the middle? Lifting Moby in this case requires a lot of force. You don't have bones. Anyway, this is the distance over which we have to exert force to lift Moby to the top. We can increase this distance by moving the fulcrum towards him. Since the distance is increased, the amount of force needed to lift him is decreased. Let's see some more levers. The fulcrum in a Class 2 lever can be found at one end with the effort applied at the other end. The load is somewhere in between. A wheelbarrow is a Class 2 lever. Since the load is close to the fulcrum, the effort needed to lift the load is spread out and lifting is easier. In both Class 1 and Class 2 levers, the effort needed to move the load is smaller than the load, but the effort travels further. Class 3 levers have a fulcrum at one end like a Class 2 lever, but in a Class 3 lever, the position of the effort and load are reversed. Here, the effort needed to move the load is actually greater than the load itself, but the load moves further than the effort. Tweezers are Class 3 levers. So is your arm. Before Moby and I understood levers, playing on a seesaw was about as much fun as waiting for a bus. But if Moby, who weighs about twice as much as me, moves halfway up the seesaw, we can balance with no problem. Ah!
On the top of page 51, you have a place to take notes, and you have 5 points. There are 3 parts to a lever: load, force, and fulcrum, which is the support or the balance. It's the part in the middle that it moves on. We have a seesaw is a lever. That's a fun lever. The center is the fulcrum. The load is your friend on the other end. You may pause the video, and resume after you finish taking notes. So next we're going to be talking about the screw. So we're going to first watch a video on the screw, and then we'll come back and take notes.
The next type of simple machine we're going to look at is called the screw. Believe it or not, a screw is adapted from the inclined plane. If you follow the thread from the tip of the screw, you'll see an inclined plane constantly curving upwards around a shaft. A screw is a simple machine used to apply tremendous force with very little effort. People use screws every day. Screws are used to hold things together. Screws are used to open and close vices and clamps. And they're used in drill bits too. The screw is better at increasing force than other simple machines. That's why a screw is used in a car jack. Each time the screw makes a complete turn, it moves a load a certain distance along the screw. The distance depends on the amount of space between each overlap of the inclined plane. The distance between any two neighboring peaks is called the pitch. In order to lift the car with a car jack, you have to turn the screw many times. With a screw, it takes a little effort to lift the car over a long distance. Here's another example. Let's say you want to put these two pieces of wood together, and you can use either a nail or a screw. Using the nail would take more force. It would take less force to turn the screw. That's because a longer distance is covered when you turn the screw. And as we've already learned, longer distance decreases the effort.
A screw is an inclined plane wrapped around a pole. It's used to hold materials together. It's also used to drill holes, and the tip is sharp. Please pause the video as you need, finish your notes, and then resume the video. Next, we're going to look at the wedge.
The next simple machine we're going to discuss is the wedge. A wedge is really an inclined plane that is used as a tool. Wedges are used to raise objects, like when you jam a door wedge under a door. It raises the door just enough and exerts a strong force against it. Wedges are also used to split objects apart. An axe is a wedge attached to a handle. Almost all cutting machines use wedges, like a saw and a knife. A pushpin uses a wedge too. A wedge is a simple machine used to raise objects or split an object apart. Because they're machines, wedges need force to make them work. How much force you need depends on the angle between the surfaces of the wedge. Let's say you're putting tent stakes into the ground. You have two to choose from. The orange plastic stake has a larger angle between the surfaces. The metal stake has a smaller angle. What stake do you think will need more force to drive it into the ground? If you were to try to put the plastic stake into the ground with your hands, you probably wouldn't be able to apply enough force. You may need a hammer to help. Putting the metal stake into the ground is easier because it requires less force. So, the smaller the angle of the wedge surface, the less effort and force you need to make wedges work.
So the wedge, the notes are on the top of page 52. Two inclined planes back to back. It's used to raise or split an object, usually a triangle shape. Please pause the video and resume after you finish taking notes.
Are you stuck in the bathroom again? Dear Tim and Moby, can you tell me about the wheel? From Valerie. The wheel is another device that falls under the category of simple machine. But we can't really talk about wheels without also talking about axles. For a wheel to do any good, it has to rotate on a rod called an axle. Like I said, the wheel and axle is a simple machine, like the lever, inclined plane, and pulley. Simple machines are the most basic tools out there. They allow us to move things more easily by magnifying our efforts. The wheel and axle is actually a rotating lever that moves in a circular motion around a fulcrum. I think somebody needs to watch the Levers movie. Okay, take this doorknob. It's a wheel and axle at work. The knob is our wheel, and this metal rod is the axle. And they turn around this point, which is called the fulcrum. Without a knob, it's pretty hard to turn the rod. It takes a lot more effort. The big knob magnifies the force of the turning motion. The wheel movement is turned into a shorter but more powerful force at the axle. You have to turn the outside of the wheel farther than you want the axle to turn, but that extra distance is translated into more turning power. It's a trade-off. Hey, good job, Moby. You've shown us that the wheel is just like a round lever. Is that my toothbrush?
Notes for wheel and axle are: wheel that turns on a post, which is the axle, helps us move heavy objects, and rolls easily. When this video ends, you will start with the next video.